10 to the power of 0. But if we have different base, assume that we have different base such as 5, then 1 to 3 means 1 times 5 to the power of 2, 2 times 5 to the power of 1, and then 3 times 1. So we have different number. Now we want to consider conversion between the two. For instance, assume that we have a number such as 1, 2, 3 to the power of anything. What number do you want? Excuse me? Let's use 7, right? Then I want to convert it with different base. What base do you want? I will use your base. What base do you want? 4. So let's convert. Then we first represent this number using our decimal system. So decimal is the middleman, but it's not the major goal. We initially represent these things in decimal, and then after decimal representation, we convert this back to 4, right? With base 4. So with decimal representation, 1 means 1 times 7 squared. 2 means 2 times 7 to the power of 1 plus 3. Then it is 49 plus 2 times 7, 14, plus 3. Then 52 plus 14, 66. Excuse me?
Oh, you actually added them. Okay.
Any questions? Then, now I want to use base 4. So 4 to the power of 0, right? 4 to the power of 0. And then 4 to the power of 1. And then 4 to the power of 2. And then 4 to the power of 3. 4 to the power of 3 is 64. We have 66 and 4 to the power of 64. It means there is 1 4 to the power of 3. Do you follow me? There is 1 4 to the power of 3. 64 is subtracted, then it is 2. So there isn't enough. This means 0 times this one. And then this isn't enough. 0 times this one, then there is 2. So with this representation, it is 1, 0, 0, 2 with base 4. So I converted using this idea. So this is the theoretical approach to convert. So last time we couldn't cover this portion. So now I will convert this one more time to base 2. So I will follow a different direction. First direction is using base 4. And then I will follow a different direction that uses base 2. With base 2, 1 times something, and then 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, 5, and then 6, right? So if you have 66, then there is 1, 2 to the power of 6, and then 0, 2 to the power of 5, 0, 2 to the power of 4, 0, 2 to the power of 3, 0, 2 to the power of 2, and then 1, 2 to the power of 1, and then 0, 2 to the power of 1. Do you follow me? So 64 is handled here, and these are empty, and then 64 plus 2 is 66, so it is 2 times this one and then 0. Then with base 2, we get 1, 0, 0, 0, 0, 1, 0. So this represents the same number. So we extract these numbers to form a number, right? So we form this number with this thing. So this is the theoretical approach. And if you don't have a question, I will mention about the algorithmic approach. Instead of theoretical approach, algorithmic approach may be more efficient or practical. But first of all, you should know that the conversion between different bases isn't theoretically very difficult. Just practical calculation might be tough, but theoretically, it's not very difficult. Any questions? Then I will show you the algorithmic approach. And all algorithmic approach, a base change depends on this simple fact. With base B, we represent, for instance, some number such as final digit, digit 0, digit 1, digit 2, and so on, and then digit, for instance, n, right? So we have this kind of number represent, for instance, 1, 2, 3. 1, 2, 3, and so on, right? So we can represent number using base B. And then the meaning of this is d to the power d0 plus d1 times base, right? And then d2 times base squared, and so on. And then d to the b to the power of n, and then dn. So this is the meaning. Do you follow me? I explained these things many times, and you get it. So this is the abbreviation of this number. Any questions? Then, this is the key to algorithmic approach, right? Algorithmic approach comes from very simple idea like this. To get B, we extract B. If we extract B, then we get some number here, and then plus D0. Do you get it? So it is the common factor B multiplied everywhere, right? B multiplied everywhere, plus the remainder D0. Do you get it? Then, now, we get D1. With D1, and then B here, we get this thing. And then, with B multiplied twice, we get D2 here, and then the same thing, B, and then we continue these steps. So D0, and then B here, and then D1, and then B here, D2, B here. So this is the actual algorithmic approach people use. And one of the famous one using this is called the binary exponentiation that I will cover very soon. But for any base it works. For any base it works. So I will solve the above problem using this approach. Technically, the only thing we need in each step is the remainder after dividing by B, right? So after dividing the whole number by B, the remainder is D0. Do you get it? So after dividing this number by B, the remainder is D0. In other words, each step, the only thing that we need is the number mod base, right? Mod base. This is all you need to do each step. And then each step, you get the remainder, D0, right? How can you get the remainder? By using mod calculator. So let's do it. So 66, and then you want to represent this thing using mod 4. So I divide this by 4. So if I divide this by 4, then by division algorithm, quotient is something, and then remainder is 2, right? So we don't care about the number above. We only care about this number. 2 is extracted, right? So first thing, our zero step thing is found, right?
Why did you pick 4? Is 4 a base that we're looking at?
Right. Someone chose 4, so I follow. And then next time, the remaining portion, the quotient portion is, for instance, if you divide 66 by 4, then it is 1, and then it's 26, and then about 6, right? And then 2, right? So I handled this remainder. That means 16 is here. 16 is here. Now, we don't care about this number. 16 divided by 4 gives us what? If you divide 16, then the remainder is 0, right? And then 4. So it is, this is the first digit number, 0th digit number first. And then, if you divide this quotient by 4, then the quotient is 1, and then the remainder is 0. remainder is 0. And then if you divide 1 by 4, then the quotient is 0, and the remainder is 1. This is the third number. So we write this in reverse order. 2 is found, right? And then 0 is found, and then 0 is found, and then 1 is found. And this is the algorithmic approach to convert. So no matter what base is given, you can do this thing. No matter what base is given. So to check it, let's do it with base 2. If we do this with base 2, 66, and then if you divide, but instead of, as you can see, instead of writing down the number in this approach, I will use similar thing that I mentioned. It is not stackable, so I will stack it. First thing, it is 66. Then, if we divide by 2, if we divide this by 2, then if we divide this by 2, then 2 times like 33, right? 33 gives us 0. 2 times 33 gives us 0. So the remainder is 0. So here, divisor or base, right? Here I wrote base, and then here I wrote quotient, and then here I write remainder, right? The remainder is written here. So I will stack this way, right? Instead of writing down equal symbol and these steps all the time, I want to create a stackable algorithm. Then the next step, I divide 2, so I will not repeat it. So I don't even need this base portion, column error, because I'm dividing by the same number. So only 2 columns will be enough, right? So if I divide this by 2, the quotient is 16, and the remainder is 1. Do you follow me or not? If you divide 33 by the base, then it is this one. And then if we divide this by 2, then 8, and then remainder is 0. If we divide 8 by 2, quotient is 4, the remainder is 0. If we divide 4, quotient is 2, the remainder is 0. If we divide this by 2, quotient is 1, and the remainder is 0. If we divide this by 2, quotient is 0, remainder is 1. Then once we arrive at 0, we are done. And then we can write this in reverse order, right? So this is the number that we can create, 1, 0, 0, 0, 0, 1. So I showed you the method of using algorithm approach instead of theoretical approach.
Would there be another 0?
Oh, I see. I see. Yeah, I couldn't see the top portion all the way up, right? So this way we can approach. So let's test it. Let's test it. So please find the binary number of this representation, 15. Please do it using the algorithm, using the stackable algorithm.
Wait, what?
Base 2. A binary means base 2. So convert this to a binary number. So after this conversion, you know that 15 is equivalent to 1111 in binary representation. Any questions? So you may doubt. So convert this thing using base 3 to test your skill. Convert this using base 3. So now base is 3, right? So divide this by 3. So it is 1 to 0. Let's confirm using theory. So by theory, this means what? 1 times 3 to the power of what? 2. And then 2 times 3 to the power of what? 1. And then 0 times 3 to the power of 0 or 1. Then, as you can see, 9 plus 6 plus 0 equals 15, right? So this method works, right? As far as these kind of things are concerned, I have never seen any book or internet page creating stackable algorithm like this. So it is not very big, but it'll help you, right? I gave you many stackable algorithms, right? And it'll help you when you need to convert something. Now, what if the number is big? Then hand calculation is very tedious. So let's briefly create some algorithm doing the calculation. In addition, I will use this algorithm in the future calculation. So I will show you how to do it. First of all, I will open a new page and then write it. For it, the input, possible input is like number itself, right? So my n will come, right? My n will be plugged in. For instance, like 1 to 3, right? This is the decimal number. And what else? Power, right? Oh, no, not the power. Yeah. I'll develop binary exponentiation. So I will write what we will do and then return back. What I will do is the binary exponentiation. Binary exponentiation is necessary because immediately after this, we will begin to cover a to the power of some number. For instance, we will begin to cover something like this. 1, 2, 3 to the power of 5, 6, 7. 5, 7, 6, right? So we will cover this kind of calculation. Then, as you can see, it's not that easy. To handle this kind of exponentiation, people developed binary exponentiation technique. And I will implement this technique using almost the same algorithm as the one that you did, right? Almost the same algorithm as the one like this. We can do this advanced exponentiation. Do you follow me? And I will explain the idea first and then begin to implement. So binary exponentiation focuses on power of 2. So assume that you ask to find the power like 5, 7, 6. Then instead of worrying about the whole power, you just find b, and then b squared, and then b squared squared. That is b to the 4th power, right? And then b to the 4th power squared, that is b to the 8th power. And then b to the 8th power squared, then b to the 16th power, right? And then 32nd power, 64th power, right? 128th power, 256th power, right? So we find the power of 2 each time of the previous one, not b itself. So we only worry about these numbers. In other words, to multiply b 576 times, instead of multiplying b 576 times, we initially find these crucial powers, right? These crucial powers. And then using these crucial powers, we create the appropriate power representing this number like binary exponentiation, like binary numbers in the power, not the product, but I will write it first. If we subtract this huge power, then 576 minus 512 gives us 4 and 6, right? 64. Then e to the 64th power. Do you get it? So instead of multiplying all the numbers 1 through 567, 76, we multiply 512 and then 5 b to the power of 64. So this is the idea behind it. But if we write the addition in the exponent, it looks like this. b 512 plus 64. Do you get it? Then if I use base 2 notation in the power, then it looks like this. So I will extract this power portion and then write it. 512 plus 64 equals 576, right? And then 5, this can be written in terms of 2 to the power of something. 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9's power multiplied by 1 plus 2 to the power of 6, 1, and then 0, right? All other places have 0, right? So this is the key. Then it looks like 1, and then 8th, 7th, 6th, right? 5th, 4th, 3rd, 2nd, 1st, and 0, right? In binary representation. So assume that you see 0, don't care, right? You don't care. Just go up, 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 up all the way. And then if you see 1, multiply, right? And then if you see 0, up, up, and then multiply. So only 2 numbers are enough to calculate this kind of power. This technique is very crucial in the following chapters. Any questions about the theory part? Of course, this isn't the algorithm itself that we will use. We will develop an algorithm to do these things, but I'm explaining the theoretical side of binary exponentiation technique. So before introducing algorithm itself, I will use this theoretical thing to calculate some power. But if we do not limit by mod, then the number will explode, right? So for instance, if you multiply 100 times, then it will become too large. So I will use mod, like mod, about 7 might be moderate, right? It's not limited, but in our hand calculation, mod 7 is very moderate. Do you follow me? In reality, like in 1 kilobit security system, we use mod some number between 0 and 2 to the power of 1024. So this is the one that we will consider. Then I want to calculate like 3 to the power of what power do you want? You can pick some 3-digit number. So pick 3-digit number. Pick any 3-digit number, then I will use your 3-digit number to show that it's not a setup. 275, right? So I want to calculate this number with mod, because without mod is possible, but without mod, the number will become very large easily, right? So to reduce the number to manageable form, I chose mod 7, but it's not limited. You can use any number here. But for our hand calculation, I reduced the mod. But in our program, we can use very big mod. Then let's do it. 275, I will find the binary exponentiation. I will find the binary representation. So if you divide by 2, then quotient is 1, 3, 7, and the remainder is 1. Do you follow me? So almost the same technique that you saw very many times, right? The only difference is non-changing quotient, right? In this case, in the past, we find the big quotient and then find the non-changing divisor, right? And then if you use the same divisor, then it is 68, and then remainder is 1. If I make a mistake, please let me know. 34, and the remainder is 0. 17, remainder is 0. And then 8, remainder is 1. 4, remainder is 0. 2, remainder is 0. 1, remainder is 1. So I could find the binary representation of the given number. So the number that you chose is 10010011 in binary representation.
Last one, shouldn't that be 1
I said thank you. You're right. So 1, and then remainder is 0, and then 0, 1. You're right. Thank you. So this portion is the quotient if you divide it, and then remainder at that step. So what does this indicate? It means all you need is the number b to the power of 0, and then b to the power of 1, and then b to the power of like 2, 3, 4, right? And then 5, 6, 7, 8, right? B to the power of 8. So all you need are these, right? All you need are these numbers, right? B to the 0 power. So these numbers are multiplied. I made a mistake. This isn't what I meant. Sorry. This is not B. It's 2. 2. Sorry. This is. I was a little bit confused between the base and. So this is what I meant. These powers are necessary, right? What I meant was these powers. In other words, 3 to the power of this number, 2 to the power of 0, right? And then 3 to the power of this number. Do you get it? So I made a mistake when I described this thing. Do you get it or not? So what I meant was this thing, right? So this is not the step doing the exact calculation. This is the power representation. So all I need is these kind of numbers, right? If you don't get it, ask me. So here, multiplication is here, but if you just collect the powers, if you just collect the powers in power notation, powers add, right? Powers add. If you collect these things, and powers add. So what does this mean? All we need to do is calculating. I will write it here. 3 to the power of 1, right? And then 3 to the power of 2. But 2, we cannot directly jump to 3 to the power of 2 to the power of 4, right? We cannot directly jump. So even though we don't like it, we need 3 to the power of 4. Do you get it? We need 3 to the power of 4. And then we need 3 to the power of 8. And then we need 3 to the power of 16. 16 is right here, right? So we need this number. Do you get it? We cannot directly jump from this to this. We need these things even though we don't use these things at all. And then the same thing happens, and then we go all the way up to 3 to the power of 256, right? So we need these things, and then this number is used. So there are like 4 different numbers that we can use. And I will indicate the numbers in the next column, unless you have a question. You should know what I'm doing, right? Theoretically and practically and algorithmically. Then let's finish it. So I will say this. Why? Because in the future, you will learn a better method. But right now, we don't care about any high power theorem, so just use it. So 3 to the power of 1 is congruent to 3 mod 7, right? Here, mod 7. Do you get it? Because 7 is the number that we can easily manage. If we use, for instance, 7,000, then mod calculation will take a long time in our hand calculation.
Why would we choose like 2?
It's possible. The 2 is too simple, then you don't see the nature. If I use like very small number, you don't see the nature. If I use a big number, we will be in trouble to really calculate. So I chose 7. Any number can be used here. Then the next number, like it or not, should be doubling this, right? Should be doubling this number, right? We should double the previous number in the power. Then 3 to the power of 2 is 9, right? 3 times 3 is 9. And 9 is congruent to what? 2 mod 7, right? 9 o'clock is the same as 2 o'clock. Then now, like it or not, 3 to the power of 4. Even though we don't use this directly, we should double the power, right? Doubling is the thing that we can do. Doubling the power is the thing that we can do. Then it is congruent to 4, right? 2 to the power of 2, 4. And then the next number is doubling the power. 4 times 4 is 16, right? 4 times 4 is 16. And then if you find the remainder after dividing by 7, what is it? 2. Then as you can see cycle, right? 2 becomes 4, 4 becomes 2, and then you see the cycle, right? So 3 to the power of 16 is, by this cycle, 4, right? And then 3 to the power of 32 is 2. And it continues, right? 3 to the power of 64 equals 4. 3 to the power of 128 equals 2. And then 3 to the power of 256 equals 4. So these are the numbers that you need. And then we don't multiply all these numbers. We selectively multiply. And where can you find the indication? Binary decomposition, right? Binary decomposition gives you the clue. And I already mentioned these things. This is needed, right? This is needed, this is needed, and then this is needed, and then top one is needed. So I will mark the necessary number. This number is needed, this number is needed, and this number is needed, and this number is needed. Then all you need to do is just multiplying 4 numbers with mod 7. So let's finish it. Three times 256 multiplied by 3 times 16 multiplied by 3 times 2 multiplied by 3 to the power of 1, right? This is nothing but 3 to the power of some number that you chose, right? 275. So this is the initial problem, but I decompose it using binary exponentiation technique. Then now these are congruent to 4, right? This is congruent to 4. 3 to the power of 16 is congruent to 4. And then 3 to the power of 2 is congruent to 2. 3 is congruent to 3. Then I will show you. 4 times 4 is already handled by the number, right? 2. And then 2 times 3 is 6. 6 is congruent to negative 1, right? 6 and negative 1 are the same. Then the answer is congruent to negative 2. Negative 2 is congruent to what? 5. So I finished it. Yes? Some student chose this high power. Yes. So any number, any power, any mod can be used, But the only reason that I chose mod 7 was hand calculation. In real programming, you are not limited to the power of like mod 7, right? And you can use any moduli to do this kind of calculation. But what I showed you was the usage of binary exponentiation technique in this brute force calculation. On the exam, I may ask you, for instance, this kind of thing. Calculate I may ask you to calculate this kind of thing. Then what should you do? Of course, I said brute force calculation. If you like brute force calculation, use brute force calculation, but there is a better method that I will cover very soon. But in any case, you need to do the calculation using mod calculation. And now I will show you the method of handling these kind of things after covering the binary exponentiation. So let's program it. So algorithm-wise, we do not follow this theoretical approach. Do you remember that I gave you algorithm that is a little bit different from this kind of approach? And I will give you the similar thing this time. So we need 3 numbers. The number, look at the problem itself. Problem itself has numbers like 3 to the power of, for instance, 275. Mod can be added anytime. So right now, let's not worry about mod in theory. In actual calculation, I use mod to reduce the number. But let's not worry about mod. Then we need 3 numbers. Base, right? And exponent, right? Exponent. I will use different column and then X. So initially, this is the initialization step. Initialization step gives us this value. Exponent is red. Base is red. X is default number 1 because we will multiply to this number. Then what is the number that you should begin with? You multiply to 1. Any number can be multiplied to 1 and it will begin to change. So this is the initialization step. Any questions? Then after this, only 2 things you need to do. Binary exponentiation means this. Assume that if you divide like this kind of number by 2, then you will see the quotient itself, right? 1, 2, 7, and the remainder, right? So if the remainder is 1, then we will. So I will write down the algorithm. If odd, right? Odd means remainder is 1. Then multiply b and x, and then store it in x. If you see the even number, that means if you divide this kind of number, then the remainder is 0. Then what you need to do is b goes up to the next level. So this is all you need to do. So this is the algorithm. This is it. This is the binary exponentiation until you reach power 0. Until you reach power 0. Each time, exponent. So you should change exponent by doing this. Because it is odd, I make even. Because we are squaring it, we should reduce the power, right? So I add the change of e part 2. So each time something changes, but not all 3 things together. Each time 2 things change. Exponents reduces following that. If it's odd, just becomes an even, right? So it is like e minus 1. That way we make e an even number. If it's an even number, then you can divide by 2. Because it's even, there is no problem. So exponent changes and the number changes. So let's do it. So take a look. Initially, this is odd, right? So what should happen in the next step? Because it's odd, x and b should be multiplied, and then, do you follow me? And then exponent should become what? 274. Almost the identical one as the previous one. And then b is kept, right? B is kept. Now, the next step, because it's even, what should we do? B should be b squared. Do you get it? And then, what is the next thing? E should be 137. And then this is kept, right? And then you can do it to practice. So you can write down these things to practice. Because it's odd, I should multiply these two numbers, then 3 to the power of 3, right? I should multiply these two numbers, and then I should reduce this number by 1. Because this is even, I should square it. And then I should divide this by 2. 68. And this doesn't. So each time there is an arrow keeping the previous number. And then because this is even, I should square it. Right? I should square it. And then I should reduce this number. Because this is even, I should square it. And then this is 17. And then I should still keep it. In fact, you don't need arrows. But to explain the idea, I'm just adding arrows. Then, because it's odd, what should you do? You multiply b and x. What is b and x multiplication? 3 to the power of 19, right? And then this number should be reduced to this number, right? 16. So you decrease this by 1. So either decreased by 1 or like divide by 2, right? Either way. Can you divide by 2 is when it's an odd? Impossible, right? So when it's an odd, just subtract 1 to make even. When it's even, divide by 2. Then, because this is even, what should you do? Even, you should square it. Because this is 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 odd, what should you do? You should multiply b and x. You should multiply b and x. Then 3 to the power of 275, right? So this is the way we create the algorithm, and then it reached 0. So this is the result, right? Do you get it? So theoretically, I showed you. Why do I cover this algorithm? Because I will make a computer program doing this exponentiation with mod. Because, as I showed you before, MATLAB itself doesn't have this function. But I need this function. So I will make a function now. Do you get it? So I will implement these things. Once we make a program, all you need to do is doing this simple thing, right? This simple routine in the calculation until it reaches 0. So as far as the number is positive, we keep doing these things, right? We check whether it's odd or even. When it's odd, we do these 2 steps. When it's even, we do these 2 steps and continue. Do you get it? So I will make a program and then modify this program. So my n is 253. My exponent is, is 3, right? My exponent is 275. And then my x, right? My x, doesn't matter. My x equals 1. So I did the initialization. Any question? I did the initialization. And then, now I will do the same steps while my exponent is positive, right? While as far as my exponent is positive, I will do either of the two actions, right? Either of the two actions. Do you get it? So, I will show you one example. Mod, for instance, 5 with 2, modulus 2. Then it gives us mod 10 with modulus 2. In other words, mod n, comma 2 determines whether it's even or odd. Do you get it? So, I will do these things. If mod my exponent 2 is equal to 1, then it means odd, right? Do you get it? Yeah, equals is used to compare two numbers.
So equals, you have two equal signs?
Yes, to compare two numbers. Because there are two different things. Equals means assignment. This value is assigned to this location, memory location, but this is not an assignment comparison. So when you have comparison, you use 2. So if this happens, what should we do? X equals, my n was not a very good choice, so I will use just my base, right? My base. My base multiplied by x. Do you get it or not? I implemented this part. I'm implementing what I wrote down, right? And then I will implement the second line too, and the second part too. So my exponent becomes my exponent minus 1. Do you get it? Otherwise, x does not change. My exponent, I will change base first. My base becomes my base over 2. And then my exponent is my exponent over 2. Then I finished, right? Thank you. So I made this part and then run it. So if I run, then it will explode, right? Because the power is too large. So I will reduce the power to a smaller number to check my program. By the way, I should write down the result. So what is the result? Result is stored in X, right? Do you get it? Result is stored in X. I will let the program write the result. So save and then run. So this is the result. Do you get it or not? This is the result that you can get. So let's check it with small numbers. For instance, with small number, like 2 to the power, what number do you like? 9. You guess the number, right? So what is 2 to the power of number 9? 10? Right? Because you already know any power is okay. 2 to the power of 7. So I followed my simple routine to do this thing. So what is the advantage of this simple program? Because of this simple program, we can do the powering, right? Do the binary exponentiation. If you don't get it, ask me. Then now, with this, there is no big difference. There is no big difference between MATLAB function and my one. But now I will add mod. So one more factor comes in. mod given by the problem, right? Mod P. So P could be given by the problem. We use 7. Do you see it? I attach this thing. Then with this one, what changes? We will change this X result, right? Mod this. Do you get it? So mod P is used, right? And then mod P is used. Then with this, I can do higher. I can use higher power. So like this kind of power is okay with this, right? So instead of wasting time, I will just use about this length number, or maybe one more digit is okay. So I save it. Can you do it? 2 or 3 is the number, like even 6 is possible, right? 6 to the power of 100 million. It will take a long time, but in binary exponentiation, it is like logarithm approach. It is extremely fast. As soon as I hit it, you'll see the result. With mod 7, between 0 and 6, right? So let's see it. So time it. Done. So this is the one embedded in your cell phones. So any number can be given. Then in our hand calculation, this P was limited to 7. But in reality, I can use very big prime, right? So like 101. Or what kind of prime? I will pick some prime. I do not know whether this memory can handle these many primes, but check it. So this is the number that I will use. 63837. This is prime. This P is prime. Then let's do it. In fact, I don't have any limitation whether this mod should be prime or not, because mod can be applied with any n, right? So in fact, this effort was not necessary, but let's do it. So can you handle this problem? 6, even this number can increase, right? This kind of number to the power of this number with mod. Very tough, right? Very tough. So how long will it take? So time it. Done. So with this kind of efficient algorithm, your cell phone can hold the program and do it. So numbers are being transmitted, right? How? We scramble, and then once it comes, it unscrambles. So I will make this program a function instead of just typing these kind of things all the time. I'll make a function. So I'll make a function, and my function will have this thing. You can name this function anyway. What name do you want? What name do you want? Like power B. Doesn't matter, right? Power B. And the input is B, right? Base, exponent, and then power exponent, and then mod, right? Right? These things are coming in. Then you should give the output, right? You should give the output x, right? I will give out x. So I will say out x. Any questions up to this point? And then my B is not necessary because it is plugged in, right? So my B will, my B is still necessary. My B. Initially, my B is B. So I make this function, and in the end, output is nothing but out x, right? So x is the output. Any questions up to this point? I made a function. And then I will save this as the same name, power b, right? Power b. I should use the same name as the one to use. So I made a function. Then from this point on, I shouldn't even open the program. Just I type whatever I have. So power b with, what is the first thing, base? Like 2, and then power 273, and then power of 275, and then mod 7, right? This is the one that we did, and then it will give us the result from this point on. And I will rely on this to check many calculations, because MATLAB didn't provide this function for us. So we create it, and we will use this function in the future. Because in the future, we need to calculate this kind of mod. In higher theoretical portion, we cover some theorems, then we need to check this. But if you have a question about any step or even programming, ask me. Then we are equipped with power b function. We are ready to cover the next chapter. But before going into the next chapter, I will indicate the importance of binary numbers. When you see these kind of things, you just see numbers, but there is a reason that we cover binary numbers heavily in number theory. Can you guess? In the past, people developed many nice ideas to communicate. And I will do something, and some of you may know. In the previous, about 3 weeks ago, I did this thing, and someone recognized. So check what I'm doing. Some of you may recognize. I did something. And what did I do? Yeah, and then I did specific thing. That's it. So this represents as 3 simple dots represent as long dots O and 3. So whenever someone threatens you to do something, then either using light or something, you can do. Then someone recognizing Morse code knows someone is in trouble or something, right? Or joking, right? But you can use flashlight to do the same thing. So people did communication using some kind of symbols, and this has great advantage. So I hit it, left it. So by using any means, you can represent 0 and 1. So when you have, for instance, electric circuit, then if the current flows, then you can call it 1. If current doesn't flow, you can call it 0 or vice versa. Anyway, it's possible. Or if it is magnetized, then it is 1. If it's not magnetized, then it's 0. That's the principle of hard drive. One more thing. If it is white, then you can call it 0, right? If it's black, you can call it 1. Where do you find it? You don't. Without this, you cannot. I will show you an example. So for instance, if you go to, so using black and white, people recognize 0 and 1. So in 3-bit space, people created, so I will magnify that portion. So it has, 7-bit. It has 7-bit spaces. So how many bits? So 7-bit space. So we're using black and white. People represent numbers. So for instance, this kind of thing, right? This kind of thing means 1, 0, 1, 1, 1, 0, 1. Of course, if you shrink it, then it looks very thin. But those barcodes consist of this kind of 7-bit and then sometimes 12-digit barcode. And then recently, they added one. And then, like beginning, and in the middle. So middle has 0, 1, 0, 1, 0 space. And has 1, 0, 1, 1, 0, 1. And then in between, these kind of numbers go in 12, usually 12 numbers. So total 95 bits are used to create barcode. So this is the application of barcode. After realizing these things, when people developed the electronic version of this barcode, they embedded the same idea in RFID chip. I cut and paste this shape and then these things. But this has far greater advantage over barcode. Barcode keeps about 12 to 13 digits. But these can hold 2 to the power of like 2K. Amazing, right? So in this structure, you can hold not just 12 digits. You can hold a lot of things. And then people are developing protocols, and now they are applying a lot of patents. Even barcode has patents. And do you know when it was initially applied? It was approved, initially applied before 1950, and it was approved in 1952. So you may learn number theory hard and then create nice algorithm using these bits and then like apply for a patent. And if your patent is crucial, who knows? All the products in the world may like mandate your scheme, right? Who knows? Then another thing is the review that we need to handle very tough chapter, very, very theoretical and tough chapter. I review a few important cases. When A is congruent to B, I mentioned this yesterday, last time. Minus A is congruent to minus B. Do you get it? Minus, plus, all these things can be handled the same way. And then multiply any K. K could be negative 2. So I mentioned these things before. And if you are asked to show that M divides something, for instance, A minus B, then this is equivalent to saying what? This is equivalent to saying A and B are congruent to mod M, right? Mod M. Do you get it? So if you are asked to show that A minus B is divided by N, then in this language, you can just say A is congruent to B mod M, or B could be 0. So in other words, A is 0, right? A is congruent to 0 mod M. I'm just reviewing some important things that you need to know. And the thing that I mentioned and then emphasized before, because we need these things in the next very, very theoretical chapter. Theoretical, but at the same time it's high-tech chapter. It covers very high-tech. 4 is congruent to 1 mod 4, right? And 13 is congruent to 1 mod 12. So generally, this direction is obvious. If it is bigger mod, if it has bigger mod, then you can easily reduce to smaller mod. This direction is not a problem. The other direction is a problem. With mod 4, can you say this the same thing? In other words, can you say this is congruent to 1 mod bigger thing, right? 12? Is it possible? Not possible, right? The other way is possible. This way is impossible. I mentioned it. I am not covering the whole detail. So we should divide by something. What should be the factor here? We should divide by GCD, right? We should divide by GCD. I mean top one. So I will indicate the thing. So instead of just giving an example, I will indicate the thing using the idea. Assume that K A is congruent to KB mod, say, M. Then my question was this. Can you say KA is congruent to B mod M? And the answer is no. The answer is no. In this form, the answer is no. Do you get it? The answer is no. So the other direction is easy, but this direction is not easy. Then we should compensate this thing using GCD. Do you get it? So when we apply cancellation law, we cannot just cancel out K. We cannot just cancel out K. If you don't get it, you can ask me, then I can give you an example. But because I covered these things before, I don't want to spend too much time on reviewing, because we have nice things to cover. But in any case, GCD of what? G means GCD of K and the number N. Right? GCD. I covered this thing before. In other words, when you apply cancellation law, be careful. Be careful. You cannot just cancel out K's and then say they are congruent. Do you understand what I mean? You cannot just cancel out. You should use smaller modulus. So I'm just reviewing important. Assume that n is prime. N is prime. Then what can you say? Prime, GCD of some number n prime is usually 1, right? So in this case, when it's prime, we can easily cancel out. When mod is, so I will write it. When n is prime, in other words, n is prime, say P, then Ka is congruent to Kb. Mod P means A is congruent to B. Mod P over GCD, but GCD happened to be 1, so still P. If K is not congruent to 0 mod P, right? Congruent, K is some number such as P or 2P or 3P, then it's useless, right? Or 0 is useless. But this is the obvious one that I mentioned before. A few more things, and then we will cover the next idea.
Is it where you say A of K is prime? Is still going to be 1?
Other prime, if it is not this prime. It doesn't have to be any prime, just any number which has GCD equal to 1 with P, given P. For instance, 11 is given, then 10, 9, anything is okay. Then it's time to cover the important thing. That is chapter 5. So here we cover very, very important theorem, Fermat theorem, or Fermat. There is a bigger theorem, so I will call this little theorem. So I will write it. Fermat's little theorem is this one. Assume that we have a to the power of p minus 1 with prime, then it is always congruent to 1 mod p unless a is 0. Of course, it's 0, then 0 is 0, right? So assume that a is not 0, meaning this, right? A is not congruent to 0 mod p. Then a to the power of p minus 1 is congruent to 1 mod p. Very big theorem. Then suddenly we can change our algorithm, our brute force algorithm, by applying this. In other words, big chunk can go to 1, right? Big chunk. For instance, someone may ask to find the power like this. Oh, find 2 to the power of right? Assume that someone asks you find this kind of power. Without Fermat's little theorem, we depends on our binary exponentiation, which is extremely, insanely fast, right? Extremely fast. But even that one is slow. Even that one is slow. Why? With this number, we can remove big chunk. Right? We can remove big chunk by using 2 to the power of 6 is congruent to what? By Fermat's little theorem, 2 to the power of 6 is congruent to what? Can you get it? By Fermat's little theorem, this is congruent to 1 mod 7. Do you get it? By Fermat's little, if you don't believe, just you can check it. But I'm giving small number mod, then you can use other method. But assume that this number is big, then without theorem is tough, right? So then 6 times something can be removed, right? So just by dividing this number by 6, we can get some remainder, right? We can get some remainder. Because 6 times something becomes 1, right? 2 to the power of 6 times something becomes 1. Only thing that we need to worry is some remainder after dividing by 6. Then between 0 and 5. That's the maximum we should worry. That means we can make our algorithm faster. But as I mentioned, binary exponentiation is fast enough. Even without any high power theorem, we can use binary exponentiation to calculate anything. But assume that I asked this on the exam. And on the exam, if you don't use Fermat's little theorem, then can you apply binary exponentiation? It's very tough, right? Computer runs it very fast, but you cannot run that fast. Then you need to use this thing to remove big chunk and then worry about small piece. So next time I will show you the proof of these things and then calculate the necessary things. And next time, because of the faculty meeting, I will end at 5:50 next time. 5 minutes earlier.